In this video and the next, I want to talk about energy, work, and heat, and basically their interconnections or interrelationships. A lot of what I'm going to talk about here, you're probably already familiar with from your previous learning. So it'll be a good review for you, a good refresher before we, go further and dive deeper into thermodynamics. So energy, as you know, can take many forms. So you can talk about thermal energy, electrical energy, chemical energy, nuclear energy, and radiant energy. So only some forms of energy you can actually see or feel. For example, if you switch on a lamp, you can actually see the energy that it produces as light, and you can probably even feel the warmth a little bit. But if you look at a microwave oven, it produces energy to cook food, but you cannot see the energy or feel the energy that it generates. So energy, more than the notion of whether you can see or feel it, it is actually defined by the change it can bring about in matter or in a body. It's defined by its effect on matter, its capability to do work. So let's look at some of these forms of energy here and see what they result from. So thermal energy, for example, results from atomic and molecular motion inside a system or inside a body. Atomic and molecular motion. So the faster the atoms and the molecules move inside a material, the greater is the thermal energy content in the material. And a very good measure for thermal energy would be the body temperature. So you can easily measure the temperature of the body at its surface and determine what the content of thermal energy in the material is. So electrical energy results from the flow of electrically charged particles. So flow of electrically charged particles. So either electrons or ions, any electrically charged particles. So for example, on a stormy night, when the ground and a cloud in the sky develop a separation of charge, the resulting flow of electrons from one to the other produces lightning. That is a form of energy, and that we call the electrical energy because it's flow of electrons. And coming to chemical energy is basically stored within a chemical compound in the chemical bonds because of the interatomic and intermolecular forces between the atoms. So how the atoms are arranged in the material, they are going to have some interatomic forces of attraction, intermolecular forces of attraction. So the energy stored in those chemical bonds is the chemical energy stored in chemical bonds. And nuclear energy is the energy stored in the nucleus of atom. And it's a very, very powerful form of energy, as we know. Stored in the nuclei of atoms. Then radiant energy is basically energy carried by light and microwaves and radio waves, etc. Energy carried by light, and light can be visible or not, microwaves, radio waves, etc. So in the last video we briefly touched on a very important property in thermodynamics, and we said it's a state function that was internal energy. And internal energy is generally denoted by either letter U or E. We're going to call it U from now on. But we said internal energy is basically a sum of potential energy and kinetic energy of all components or all particles in the system, all components in the system. And if you look at all these different forms of energy that we've talked about here, chemical energy, electrical energy, and nuclear energy, these three here are different forms of what we call potential energy. So this is potential energy of a body, and which is basically the energy stored in an object because of the relative positions or orientations of its particles. That is how the atoms are arranged inside a material. What is the nuclear and electronic configuration? So this is the energy based on how the system is configured, their positions and orientations. So this will be chemical, nuclear, electrical, You can even say magnetic and so on, magnetic. So now coming to the kinetic energy, you've learned earlier that it is the energy of the body by virtue of its motion. So if you have, let's say, a car um, that has a mass m and it's moving with a velocity v, so then we say that its kinetic energy is half mv squared. And that's how you've learned in your physics lessons earlier. So now when the body is at rest, you might actually be tempted to say that the kinetic energy of this body is zero because the velocity of the body as a whole is zero. But that's not true, because even at rest, atoms and molecules inside the body, inside an object, are constantly in motion. So either if you take a solid, and we know that solid atoms are, let's say it's a crystalline solid, then the atoms are arranged in a regular fashion, and they are sitting at their certain mean positions, and in a solid the atoms actually are constantly vibrating about their mean positions, so they're going back and forth, vibrating, and they're not necessarily moving around because they don't have, they're kind of stuck in their positions. But if you take gases or liquids, you have atoms moving around, they're like sliding past one another, they're bombarding into each other, and each one of these atoms and molecules have a certain velocity associated with them. And so all these particles have certain kinetic energies, and there is an average kinetic energy for the entire object. So we actually called this energy thermal energy before, when we were talking about forms of energy here. So basically, when we talk about kinetic energy as part of internal energy of any body in thermodynamics, what we mean by that is we mean that kinetic energy is the thermal energy content in the system, and the temperature of the system that we can measure as a macroscopic property is the measure of this thermal energy or this kinetic energy as part of the internal energy. So I hope you've now got a good hang of what internal energy of a system is. It is basically the total energy content in the system because of the both the positions or the configuration of how a system is, and also by the motion of the particles within the system, atoms and molecules. So it is the total energy content of a body. So now we've seen all these forms of energy. What is really important to realize here is that energy can actually be converted from one form to another, but the total amount of energy in the universe remains constant. So basically, energy cannot be created or destroyed. Or what I mean by that is, if you take a simple example of lighting a matchstick. So for example, when you light a matchstick, you're generating light and heat energy, but in reality you're not actually creating this energy fresh. What you're doing is you're just converting the chemical energy stored in the matchstick into heat and light by doing some mechanical work. You're striking the matchstick against the matchbox, or against the side of the matchbox. So you're doing some mechanical work and converting one form of the energy into another. So we'll move on. We'll talk about the other two important concepts of heat and work in the next video, and also about the interconnections between energy, work, and heat.